UKMARS, UK Micromouse and Robotics Society, was founded in 2017 with the aim of promoting interest in small robotics activities in the UK. We have an active membership, monthly online meetings, and we run a number of events throughout the year. These include a conference, our main contest in the summer, and an autumn event where we get to run contests and catch up with each other's progress. To form a practical focus point, we decided to design a robot platform that would provide a basis for a number of small robot events and for general research use. We wanted it to be inexpensive and make use wherever possible of readily available parts. The somewhat modular design makes it possible to add different sensor assemblies, alternative processor options, and a variety of motor drives. That robot is UKMARSBOT. A robot's no good without software, so today we're going to look at some aspects of the newest code available for the robot, the Mazerunner Core. Having a versatile and easy to use robot's one thing, making it perform tasks is another. To give builders the best chance of getting results quickly, I wrote a whole bunch of software for it. I knew what I wanted and I knew what I needed. What I failed to do was distinguish between the need and the want. As a result, there's a bit of everything, and that can only be confusing to the novice or newcomer. There are two main software projects. One is a set of examples illustrating how to set up and use the various features of the robot. The other, UKMARSBOT Mazerunner, is a comprehensive project containing examples, tests and configuration code, as well as most of what is needed to make a working Micromouse robot or line follower. All of this is in a relatively large project consisting of many files that are not well organised. From the perspective of the newcomer, this will be very daunting, even if they have good programming skills. A while back, I decided to create a new software project for UKMARSBOT that would hopefully provide a better starting point. The aim was to simplify the code as much as possible, while still providing a solid basis for extension and expansion. There would be no point in creating a dead end for developers. It was also clear that many builders wanted to use different processor hardware, and that there is always the possibility of building a completely different robot while still wanting to use much of the existing software. Thus, portability was also a major aim. With these thoughts in mind, I could lay out the key requirements for the new software. Some are needed, some are wanted, but this time I hope to get a better balance. While the overriding requirement was to simplify the code, that could still be done while improving some of the features. I was keen to ensure that portability was improved. Not only should it be easier to move the code to different hardware, I wanted to make it easy to run several robots from the same code base and in a variety of events. If you have a fleet of robots, as in a club or school, this would make things a lot easier to manage, so flexible configuration options are important. The provision of the external serial port on UKMARSBOT makes it easy to attach a Bluetooth module, like that in the HC05. That makes it easy to have the builder use an always-on command line interface to issue commands and get telemetry and reporting back without having to connect a computer and reset the processor. Many builders still use the Arduino IDE for development, so the code must build in that environment. Library management is sometimes awkward, so the software must use no additional libraries. That will also make it easier to port to another environment, or a language or processor. I took advantage of the chance to write new code to manipulate the maze data in the hope that it's a little easier to understand and modify. Through all of this, I wanted to make sure the user always has easy options to extend the software for more sophisticated use. Robot configuration has several aspects that I've divided into three sections. First is the robot hardware. This deals with the processor used, the associated pin assignments, and the physical details of the controller board, but excludes things like the drive system. This is the lowest level of configuration and will probably include implementations for some aspects of the board, such as how to set and reset pins and provide interrupt-safe access to variables. Things like ADC configuration are not terribly important, so there's no direct association of ADC channels with specific sensors from the perspective of the high-level code. With other configuration options the same, there still needs to be a way to have different settings for the conditions and different events. For example, the wall sensor calibration will need to be different from practice at home compared to a real contest maze. A simple choice can be made that enables the relevant configuration. Most of the configuration is related to the actual robot. That is, the combination of control board, sensors and drive unit. Each robot can have its own config file where the physical characteristics of the robot are stored along with the various settings for each event. Many constants used by the software are also pre-calculated here by the compiler to save processor time elsewhere. This is also where the sensor readings are associated with a particular channel in a device-independent way. The ADC results are just stored in an array, and the config file tells the code which array element to use for each sensor. You can see how these things are put together in the main config file for the code. We start off by deciding which hardware platform we're going to support. In this case, there is only the UKMARSBOT 1.3a board, but if you had an older board or a different or custom board, you could add it here and then select it. Selecting the particular hardware platform pulls in a hardware-specific config file. So if we have a quick look at that, you can see that in there we have the individual pin numbers for the various functions of the robot. We have names for the channels used by the ADC, and we have some other items which are specific to that board. So in this case we have the thresholds for the ADC converter connected to the switches. Since the UKMARSBOT 1.3 board is based on the Arduino Nano and uses the ATmega 328, this is an opportunity to provide some features which are specific to that device. So here is a set of code for providing fast read and write access to the input pins. And here we have a section which allows you to get safe access to multi-byte variables which may be modified during an interrupt routine. Back in the main config file, the next section we come across is where we get to define the event. This robot has run at home for practice, it's run in the UK contest, it's run in Portugal, and it's run in APEC in the United States, and so there are settings for each of these events. At this stage we select the event, and we may just choose to have a global goal associated with that particular event. The actual value chosen is used later in the individual robot configuration file, and that's the next section. At the moment in this code I have settings for two physical robots, one called Orion and one called Core Osmium. The work that I've been doing lately is on robot Orion, and so I have the names of the available robots, I have a selection process here, and then I can pull in the configuration file related specifically to robot Orion. In the Orion configuration file, and all the robot configuration files share the exact same structure, but in this particular file I see that I'm using the home practice event, and for that I have particular values for the sensor calibrations. I have some threshold values which tell me when I need to turn, and for other events I have other calibration values. A little later I have the opportunity to define which pins, these are kind of an indirection, which pins are going to be used for different functions. I can also say which of the ADC channel numbers is being used for the various sensors. I can set the baud rate, the distance that the mouse has to travel to get from the back wall to the front wall, and most importantly we come to physical constants associated with the robot. So we've got things like the wheel diameter and the gear ratio and how wide the mouse is, and these values, these constants are all pre-calculated by the compiler for us, and they just save a bit of time later by entering the basic dimensions all of these other things get calculated automatically. We can also use the method described in another video to find the time constants and gain of the system for forward and rotational motion. And if we do that, we can then pre-calculate all the various controller constants. Again, these details are shown in another video referenced above. Finally, we have performance constants, where for this robot we might say we can achieve a search speed of 400 millimeters per second or whatever. Other robots, other speeds. Everything to do with the robot and its behaviour is defined in one configuration file, and different robots have the exact same structure but different values. I've tried to develop the software as a layered system. The idea is that each layer has a set of concerns and can only communicate with the layer above or below it. Queries can be made of the layer below and results provided to the layer above. In this way, layers can be modified or extended without affecting the rest of the code, as long as the interface is maintained. Overall, the software implements a Micromouse robot. The mouse need know nothing of the motors used to drive it. At that level, it needs only concern itself with the operations in and on the maze, user interaction, path planning and execution. Motion control is handled by a separate layer, which understands more about the capabilities of the robot and implements a basic drive system capable of controlling forward and rotational movement. It looks after the overall acceleration, speeds and positions, and ensures that the demands from the mouse are met. The motion controllers set the desired forward and rotational velocities for the robot and just assume that they will be achieved by the drive system. It's unconcerned with how that happens. It's the job of the motor controller to take these speeds and turn them into actual commands for the motors. Here is where the actual control is implemented. This is the section that guarantees that the demands for speed and position are all satisfied. Up to a point, if you want to change the drive system to a car-like platform, for instance, you should only have to change this section of the code. In general, portability would be enhanced by separating out another layer for the hardware PWM. This has not been done yet to reduce the number of files, but it only amounts to 2 functions. While not quite there yet, the overall aim is to limit the scope of each layer or section of the code. Extensibility is then a question of building upon the features provided by the other layers. For example, much of the code needed to create a line follower is going to be common to that needed by a Micromouse. Most of that is in the task. There will be differences in how the sensor data is interpreted and how to respond. Mapping and localization are different, as are path planning and execution. These are all behavioural aspects of the code and can be implemented independently of the robot platform, as long as it's able to provide the required inputs and outputs. I might expect that a potential line runner codebase would only need some different configuration settings and to replace mouse.h with follower.h. The basic UKMARSBOT platform has a dip switch and button that allow the user to select up to 16 tasks and start or stop them with a button press. This seems flexible until you want to use the robot in a more interactive fashion, such as viewing sensor readings or looking at the map. The serial interface provided by the Arduino has 2 major limitations. The most obvious is the cable, which prevents movement and interferes with positioning for sensor calibration. The other is that the processor resets whenever it's connected. Adding a permanently connected Bluetooth module lets you communicate by radio and makes for a much more flexible user interface. You can start tasks such as sensor calibration and receive the results immediately. Real-time telemetry and activity logging is also easy. By providing a number of predefined reports, it's easier to share data and compare results. The serial I/O has been made more flexible so that it's possible to log to other devices if required. I've also implemented simple selection by occluding the sensors. This is very useful when starting the robot in the maze without physically disturbing it. The more ambitious might add a display device using I2C, and the wheel encoders can be used as inputs as well. I hope that these features, and other features you can find in the code, will serve to illustrate how it might be possible to create and use a codebase that is simpler in structure, easier to understand and maintain, while providing for future expansion. By having features separated out into clear functional blocks with well-defined interfaces, it's a much easier task to locate the proper place to make changes. Where possible, this functional block should make a clear distinction between the hardware and the functions that use it. That way, it's easier to identify which parts of the code need attention when porting to new hardware. For the non-C or C++ user, the same approach will help in development and will be easier to identify blocks of code that can be translated and tested piecemeal for another language or environment. Maintaining the general structure will make it easier to work with others, even if they're not using the same hardware or even the same language. For those with many robots, whether they're individuals or groups, the configuration method should make it easier to manage the individual robots while maintaining essentially the same core software. You might note that the current state of the code does not entirely fit these requirements, as there's a balance between full implementation and convenience for users of the Arduino IDE. Much of the code is derived from the original UKMARSBOT Mazerunner code, but there have now been so many changes that it should be regarded not as a development but as a whole new project. Development has been done using Platform I/O in Visual Studio Code, as this provides the most flexible option. When you download it, the main project directory is set up as a Platform I/O project, and you'll probably have to edit the platformio.ini file for your local environment. I've also ensured that the code will build in the current Arduino desktop IDEs. Ideally, I would have split the objects up a little more finely, but I wanted to ensure that the files that make up the project are all visible in the default IDE layout on a 1920 by 1080 screen. Arduino IDE users need only open the Mazerunner Core directory inside the project directory, and it should load up without fuss. There are no external dependencies and no libraries to worry about. The project is maintained on GitHub, and I welcome any contributions. Ideally, you would make a fork of the project on GitHub, make your changes, and generate a pull request. If that's not your cup of tea, then please use the issue system in GitHub to suggest corrections or improvements. That way, everyone can see and contribute to the project in a more open manner. The project is still under active development, so you should expect changes frequently. I hope to create a stable release soon that can be used as a common reference point. So let's have a look at a live demonstration of the code running on a stock UKMARSBOT build. This is the Orion robot that's run in a couple of recent contests in various places. The code run in those contests isn't the actual Mazerunner Core code and has many more features. Even so, I want to show that the Mazerunner Core will run on the same hardware and provides all the basics needed to get you running in the maze. So we'll start off by flashing the code to the robot. Flashing the code generates a pile of garbage on the Bluetooth screen. You can ignore that. But you can see that the robot has now reset, and we'll just see that the wall information is appropriate. If I want to be safe and sure, I can always reset it and check again. At this point now you can start the mouse either by using the switches and pressing the button to set it going, or of course we have the function commands available over Bluetooth. So I'll use F2, and the robot sits waiting for me to start it off. I'll place it in the maze and let it go. While it runs, it generates telemetry telling you where it is, where it's pointing, and any other information that you might wish it to send. When it's found the goal, it tells you, and then carries on looking to see if there's a better route. all the while we have telemetry coming from the robot. So now we've finished our exploration, and hopefully the robot's got a good idea of what's going on. Let's have a look at the walls. And that appears to be a good representation of the map that we have. The map is ready for use. We can see how the mouse has flooded it by asking it what costs it has. Or if you prefer, you can ask it what directions it will use when it next runs. So let's set it going again. F2, press return. You can just about see the light flashing to tell me to get it ready. And now it should take the best path. The telemetry is still running, of course. And then return to the start. Job done. Clearly you'd want it to be running faster than that, but I have to leave you something to do. Mazerunner Core is neither finished nor is it the end of the road for Micromouse development with UKMARSBOT and similar hardware. Rather, it's a beginning for future development. As it stands, it provides what I think is a bare minimum of functionality for Micromouse builders. I don't intend to add much, if anything, in the way of performance enhancements. After all, as an educational tool, it's meant to just get builders off to a sound start. It's up to individuals to work out how to run faster and more reliably. Mazerunner Core is an application-level codebase. I hope to have available separate projects designed especially for testing and configuration of the robot. This will let builders work out the key parameters for their robot and then use those in the Micromouse code. For some, there's an interest in using different processor boards and possibly different languages. I would hope that the Mazerunner Core code might provide inspiration for a better code structure regardless of the platform. Some effort has been made to make the porting to other hardware and other languages a little easier. For future contests, you should be able to see at least one demonstrator robot running the Mazerunner Core, and hopefully others using enhanced versions. Assuming the code structure finds a positive response, I'd also like to look at developing a line follower using the very similar model. All of this would be a whole lot more fun if there were several more contributors. Well, that's more than enough from me. It's probably a lot to digest in one sitting, and examples in C and C++ are not everyone's idea of fun. Even so, it's a good time to ask if there are any questions or observations on what you've seen so far. I also welcome direct emails on more general aspects of the code, but the greatest gain would come from open discussion on the UKMARS mailing list or via issues raised in the repository on GitHub. If there are no objections, I would like to move the Mazerunner Core software to the UKMARS account on GitHub and make it and the proposed setup test software, along with any line runner core, the primary code base for UKMARSBOT. Links to the repositories are on the final slide. Thank you. If you want to have a detailed look for yourself, this is where you can find the repositories referred to in the previous slides.